This lecture is about the design of artificial lighting for a good lighting quality with limited energy use. Welcome. Very often, natural light has to be complemented with artificial lighting. Artificial lighting is needed in all buildings. You have learned about the illuminance, which is the light level on the surface under observation, a desk in an office, for instance. A lamp emits light, and this is measured in terms of luminance L in lumen. Not all this light is falling on the desk, but only a part of it. The fraction of light falling on the desk is called the coefficient of utilization, Cu. You can imagine that Cu is much smaller in case of the fluorescent lamp left than in case of the LED lamp right, for which almost all light is directed towards the desk. Next to this Cu, there is also the light loss factor, Fl, which is a depreciation factor correcting for the rated luminance of the lamp at the start of its life. When the lamp is aging, its luminance decreases because of deterioration of components and voltage variations. Fl corrects for this in order to work with the average luminance over the service life of the lamp. So, finally, the illuminance on the desk is the luminance of the lamp times the utilization factor times the light loss factor divided by the area of the desk. And how does that relate to needed electrical power? Well, the electrical power P is the illuminance L in lumen divided by the luminous efficacy. Let's look at some typical values of luminous efficacy and light loss factors. As you probably already know, the old incandescent light bulbs have a very poor luminous efficacy, as 1 watt electricity would deliver only 13 to 18 lumen, which is about 10 times less than a sodium vapor lamp. Also observe that LED lamps are very efficient, but still a bit less efficient than these sodium lamps. Sodium vapor lamps are often used along roads and in industrial greenhouses. As it comes to the light loss factors, they are given here as an indication. They of course depend a lot on the exact type and brand. Let's now have a look at natural light levels and at the levels needed in buildings to perform certain tasks. Let's start left with outdoor light levels. The illuminance from the sun itself is around 100,000 lux, while the illuminance on Earth in full daylight is around 10,000 lux, going down to 1,000 lux for an overcast day and 10 lux at twilight. To give a comparison, close to a window indoors during day, the light level will be around 1,000 lux, and far from the window it will decrease to 25 to 50 lux. Of course, this fully depends on the solar radiation on the window, the type of glazing and the size of the window, so it is just an indication of magnitude. If we now look at the light levels needed inside buildings, we see enormous differences depending on the activity to be performed, starting to 50 lux in the parking up to 100,000 of lux for an operating table in a hospital. In general, the more precise the work to be done, the higher the illuminance. For instance, in public areas in buildings like lobbies, toilets, stairwells, elevators and corridors, 200 lux is sufficient, while for office work 500 lux would be needed. Detailed drawing or mechanical work would ask more than 1500 lux. Be aware that these values are indicative and may differ according to national standards. And of course, not only the illuminance is of importance, but also the color of the light and the glare factor, which are not treated here. Let's take the example of a classroom of 50 square meters. In general, fluorescent lamps are used in classrooms because of their relatively high luminous efficacy and low price. Let's assume a coefficient of utilization of 0.6. We would like to know which electrical power is needed for the lighting of this classroom. To do that, we'll use the information of the precedent slides. From slide 4, we know that the luminous efficacy eta of fluorescent lamps is between 45 and 75 lumen per watt. We choose modern lamps with an efficacy of 75 lumen per watt. From the same table, we know that the light loss factor FL is 0.8. From the slide after, we know that a classroom needs 500 lux. By now, using the formula on slide 3, we can calculate the luminance L, which is the illuminance times the surface area divided by Cu and Fl, leading to a total luminance of 52,083 lumen. With this luminance and the luminous efficacy, we can deduce the power, which is L divided by eta, leading to 694 watt. And you may remember from another course that to obtain the quantity of electricity consumed, you just need to multiply the power by the number of hours it is on. So, if the lights are on for 8 hours a day, 5,552 watt-hours are needed a day. What can we do to reduce this electricity consumption while ensuring a good visual quality? Well, taking care that as much as possible daylight enters the classroom during the day is a very efficient measure. If the windows are large enough and the classroom is not too deep, there will be days for which the electrical consumption for lighting may be zero. The lights will be off all day. There is software like Radiance or Dialux calculating the so-called daylight factor. The daylight factor at a certain place indoors is the percentage of illuminance by natural light at that place and the illuminance outdoor. In short, it says something about how much light penetrates into the building in certain sky conditions, like sunny or overcast. You see here an example of the daylight factors for a single-floor square building with a window on all facades. What you see is the floor plan. On the picture left, you see clearly that the daylight factor is high close to the windows and decreases rapidly in the middle of the room. In the configuration in the middle, a roof window was placed in the middle of the roof, and in the picture right, reflective glass was used, allowing much less light to penetrate the building. Instead of using a roof window, you can use a natural light tube, sometimes called light tunnel. Of course, you cannot view the sky this way, but it allows to bring natural light into spaces without windows, like corridors, cellars, toilets, etc., saving this way energy while creating a nice light climate. Such a light tube is coated inside with a high reflective coating, bringing the light into the house through multiple reflections. Because natural light levels varies a lot during the day, it is best to use dimmers. These dimmers control the luminance of the lighting. If you need 500 lux and it is dark, the lamp will give 500 lux. If there is 200 lux natural light coming in, the lighting can be dimmed to 300 lux, bringing only what is needed. An additional advantage of dimming may be that in the evening you can lower the light levels, helping with the production of melatonin needed for a good night's sleep, as you have learned in another lecture. Old dimmers did not help with energy saving, as the same power was needed in full power state as in dimmed state. The dimmer was just a heat resistance dissipating the power into heat. On the contrary, modern dimmers use power intermittently, saving this way a lot of electrical energy. Next to dimming, there are other possibilities to create a good visual quality while saving energy, like controlling the switching of the lamps according to their position and the occupancy, instead of just switching all lamps in a room on and off. You see on the picture the floor plan of a classroom with tables and chairs. On the left there are 3 large windows and on the right the doors to the corridor. A classical configuration for the lamps would be this one. You now see the position of the lamps as if looking at them from the ceiling, looking downwards. There is one switch to switch all of them on and off at one time. This is very nice when the classroom is fully occupied and it is dark outside. But if only half of the classroom is occupied, this is a big wastage of energy. It would be much better to control the lighting in 2 or 3 zones, switching only the light on where needed. You see here an example with 2 zones. There is 1 switch per zone. Another possibility is to account for the fact that close to the window there is much more natural light than far away. That is why the zoning is very often done the other way around, like this. Ideally there would be 4 zones, just like that, but that is more expensive, more switches and more wires. Note that you can find nowadays also lamps with automated dimmers integrated. The light level is then controlled automatically depending on the natural light. If you equip the lamps in the row close to the window with such automated dimmers, then configuration 1 is very efficient as well. To summarize this lecture, artificial lighting is needed when the natural light is not sufficient, and you have learned about recommended light levels and how to estimate the needed artificial lighting power. You have also learned how to save electricity by making maximum use of natural daylight from windows, using dimmers, and by controlling the lights using appropriate zoning, accounting for occupancy and windows. I hope you have enjoyed it. Thank you for your attention.